I'm Juan Villegas. I'm a postdoctoral fellow in the University of Geneva, under the direction of Professor Dr. Martin Patel. I'm going to present some results on my project related to the production of processable sugars from lignocellulosic biomass. This project was funded by a multinational food company that wanted alternative feedstocks to their packaging material, sustainable in a sense, carbon-friendlier material. So the project was based on two premises. First, we cannot use material that can compete with food. That's because we selected lignocellulosic feedstocks, that is energy crops or agricultural residues. And the second premise is that the most important part, the bottleneck of the production of materials and fuels from lignocellulosic biomass is the pretreatment step. Pretreatment is some sort of physicochemical process in which we liberate the sugars from the complex polymers of the biomass. So basically, these type of processes are performed in conjunction with biotechnological or enzymatic processes. So we selected some of these physicochemical alternatives, like dilute acid, the usual suspect, steam explosion, liquid water, ammonia pyrite explosion, steam explosion at different severities, organosolved pretreatment, and combine these pretreatments with some hydrolysis of the solid portion of the biomass. Alternative to this, we compared also some mild hydrothermal pretreatment with a harsher super and subcritical water hydrolysis. I will explain that later. So basically, if we can term it like that, we define some like lignocellulosic sugar mills in which we define a fixed processing capacity. We compare different processes to pretreat the biomass and to hydrolyze the solid cellulose part. And then we deliver a final syrup of sugars that can be sold to any further bioprocessing facility. These sugars, of course, have different qualities and different properties depending on the process that we follow. We assume also that we will burn the lignin-rich residue that remains after the pretreatment to provide for heat and power for the lignocellulosic sugar mill. We are literature data, peer-reviewed data. We use process simulators such as Aspen Plus and commercial pinch energy analyzers to integrate the process. And we use all this data to feed some techno-economical and environmental models to determine the sustainability of the process. In this presentation, I will only show you the techno-economic results. So we decided, based on literature and surveys, the different conditions of the processes. We model some hydrothermal pretreatment, either using acid catalyst or only temperature and pressure to liberate the sugars from the lignocellulose. We also compare other pretreatments such as ammonia fever explosion, in which we inject a liquid compressed ammonia to alter the properties of the lignocellulosic biomass, and then try to recover the ammonia using steam stripping, water quenching, and recompression. So we have at the end a solid outlet in which there is no free hemicellulose stream. So we need to think that if we have an apex pretreatment, we will need to supplement the enzymatic hydrolysis part with the silanalysis and other enzymes. So it's not the same enzymatic cocktail for each kind of pretreatment. So we assume that also. We also investigate the organosolvent pretreatment, in which we add organic solvent, in this case ethanol, because it's easier to recover, and in order to delignify the lignocellulosic biomass. This kind of process produces a highly pure lignin stream that is a shame to burn only to provide energy. But we can also, at this harsh condition, we degrade part of the sugars into inhibitors, but that can be eventually recovered in a relatively pure form and be also co-products of the biorefinery. As I said before, we also compare some alternatives, like using hydrothermal pretreatments combined with supercritical with separation of the hemicellulose, supercritical pretreatment on the cellulose fraction, and subcritical pretreatment to produce glucose monomers. This is indeed a process that is being hyped lately too much by an American company, Rematics. I will came about this later. So we decided to model the process, and we compare the sugar yields compared to the maximum potential of sugar that I can obtain from the biomass per ton of dry biomass. As we see the red section of the bars is the easily fermentable C6 sugars. We can see that in terms of C6 sugar recovery, more or less all the pretreatments perform relatively the same, except perhaps for the supercritical water pretreatment, in which a lot of the sugars are degraded into inhibitors such as furfural, hydroxymethylfurfural, formic acid, etc. Organosol also degrades some of the sugars, but some of them can be recovered as a furfural co-product. So, but if we think a complete biorefinery, we will need to recover most of the sugars, not only the C6 sugars. And in that sense, you can see that if we use dilute acid or ammonium fever explosion, we have a higher recovery compared to the maximum potential. This is in terms of yields, but in terms of energy, this is a highly complicated graph, but I will explain it. In the upper part of the graph, we have the energy, primary energy demand, allocated exergetically to the heat and the electricity. We can see that most of the project and most of the process, the pretreatment itself is a very important part, the blue section of the bars, but the evaporation of the sugars takes out a lot of the energy of the demand. In the lower part of the graphic, we see the internal energy. That is, the orange section of the graphs is related to the lignin-rich residue born for cogeneration. And the blue part represents the energy that I can recover potentially from energy integration. So basically, we can use the secondary steam from the flash after the steam explosion and use part of this heat to using the evaporator trains to produce the concentrated syrup. We can use also the outlet of the supercritical reactor and recover quite a lot of the energy that I'm using to produce the sugars. You see the triangles, and the trend that follows them represents the net fossil energy that I will need to produce the sugars, 1 ton of sugar. As you can see, the steam explosion pretreatments doesn't need additional fossil fuel. That's because we use a high solid throughput with this pretreatment. We use concentrations in the reactor of 50% of solids. So we need substantially less steam to produce the sugars. And In apex retreatment, we have a low demand of energy, but after the enzymatic hydrolysis, some of the lignin dissolves into the syrup. So we lost a potential for energy recovery. We need, therefore, additional fossil fuel. The organosolv pretreatment also needs a lot of energy because we have to recover the fulcral and recover also the ethanol solvent. This is a those are highly demanding processes. So that is energy, but how about cost? These are the inside battery limited costs. That is the cost, the capital cost, not including utilities and cogeneration. So we see that in general, hydrothermal pretreatment that doesn't use catalyst as the uric acid need less capital investment. That is due because we have simpler setups, and also we have smaller reactors. We see, for example, in supercritical water, when we are replacing the enzymatic hydrolysis step with the supercritical hydrolysis, we have reactors of seconds, of residence times of seconds, compared to reactors that have the residence times of days. So we achieve highly important reductions in capital costs. Organosolv, due to the recovery columns, needs significantly more capital investment. Regarding variable costs, more or less all of the pretreatments performs the same. The costs are obviously driven by the feedstock cost. Feedstock cost is very important. And also, when enzyme is involved, enzymes also has a relatively high share in the variable cost. But these early stage assessments are very uncertain. In capital cost, we can go, we have an accuracy of these estimates of minus 15 to plus 45%. Also, the price of the biomass that you are procuring is a big if. Biomass is subject to disrupts, quality, availability. So we don't know what will be the final cost of the biomass. We can say that we are dealing with residues, but they are not residues anymore. They are a resource that will increase in time. So we also evaluate different values of this in a full factorial design of these parameters and determine a sensitivity analysis to see where the models are more sensible. For example, we can see that the capital cost and the biomass price has a very big impact in the viability of the process. This has been done for other systems also. And we came out with a comparison in terms of minimum sugar selling price. That is the price that makes the net present value zero. As we can see, the supercritical water pretreatment is the worst in terms of economical feasibility. That is due to the low yields that are reported in the literature about this process. So we have biomass, and we lost a lot of the sugars into the air. When I presented these results in the AGEMA conference in June, there was this representative of Rematics there. He was not very happy with the results, but the hard fact is that there is no peer review that say that we don't lose a lot of sugars with supercritical hydrolysis. So it's all this. You see that also organosolv is quite expensive compared to the other systems, but that depends. We analyze this assuming that we are burning the lignin, but the lignin is a product in itself in organosolv because it's purer. So we consulted with some experts about the possible prices of the ton of pure lignin coming from organosulfate pretreatment. And we run a sensitivity analysis in which we see that there is a high interest in valorizing this lignin if we will achieve a competitivity with the sugar product. So this was an economic assessment based on US assumptions. But what happens if we choose another feedstocks? What happens if we choose another countries? So we made an analysis in which we compare different scenarios: US, Brazil, Europe, China, India, Southeast Asia, the usual suspects. And for each country, we selected some feedstocks. And after that, we came out with these assumptions. For each regional scenario, we choose different local context economic parameters, like the cost of energy, the cost of materials, the labor, and the cost of the biomass, especially. And we can say that about this. For example, comparing the US and the European scenario, which are fairly similar regarding biomass portfolio and macroeconomic constraints, we see that European production is higher in prices. That is because the higher energy prices, also because the most abundant biomass wheat straw is not a very suitable feedstock compared with others, because the carbohydrate content is less. We can say also that feedstocks such as bagasse in Brazil and similar agro-industrial residues seems to be the more economical options. You can say also there is some constraints. In Brazil, you have still a lot of potential for expansion without affecting the rainforest. Whereas in Thailand, for example, if we want to expand the production of different bunches into the rainforest, that will be a ecological nightmare. That's all. We can say that supercritical is guilty until the contrary is proven. That the minimum sugar selling price is very sensitive to the yield and the feedstock cost, and that there is a misread interest in valorizing all the sugars and the lignin to achieve competitivity. Also, Brazil and the developing world seems to be the places to be producing biomass, bio-based products right now. Thank you very much.
Thank you very much. So, for the question. Yeah.
Can I ask you, how did you calculate this? What was your methodology?
The methodology, I use built-in information in Aspen Plus Analyzer. I also use literature, for example, for the dilute acid process, I use the general costing. For organosulfate, I also use peer-reviewed data that was provided by industry. So I combine the built-in capital cost in Aspen with more specific information.
Okay, and another question. How did you decide the uncertainty ranges for your capital cost afterwards?
Sorry?
How did you decide that the uncertainty ranges would be from?
Okay, that was a very simple, like textbook decision. If you see the Thornton manual on process design, they say like these ranges of accuracy depending on the stage of the evaluation process. For early stage processes, the accuracy that is normally used is that. So I use that.
So you didn't add the uncertainties from the peer review, the literature?
No, I just capital cost, prices of energy, prices of enzyme.
For which year? Because I didn't see.
Probably is 2012 years. All the economic data is put in $2012.
Okay.
Next, In terms of recovery, I know that, so you talked about in organosolv, you looked at the ammonia recovery. In dilute acid pretreatment, are the prices that you use, is that including acid recovery? And if so, how much of the energy cost is going to the acid recovery?
No, and for dilute acid, it doesn't consider acid recovery because in dilute acid, the percentage is too low. In reality, it's more a catalyst because in ammonia process, you inject really a lot of ammonia in there, so you have interest to recover also for the organosolv product. But it's not economical. It will not be economically viable to recover the acid.
About capital cost estimation. You said you have used the literature data, so you have actually built your own process in Aspen Plus or other software, and you have calculated the optimized process or something else?
No, I didn't optimize. I just modeled the process in Aspen. For capital cost, I take values from the built-in Aspen process economic analyzer and the literature, but I didn't optimize. I just, after that, I do energy integration with pinch analysis, but I didn't optimize.
Okay, so thank